Hello friends, so welcome to lecture 12 of this course Essential Mathematics for Machine Learning. In last lecture we have learned about singular value decomposition. In this lecture we will continue singular value decomposition and we will see some of the properties and applications of singular value decomposition. In the later part of this lecture we will define various matrix norms. So, first let us understand the geometrical interpretation of singular value decomposition. So, just look here. Suppose I am having a unit circle and these two vectors, one is blue and another one is red. So, I am having these two vectors. If I apply a transformation A, which may be a rectangular matrix also, then this particular circle transform into this ellipse having this orientation. Now, what is meaning of that in terms of singular value decomposition? So, as you know that singular value decomposition is A equals to U sigma V transpose. So, V star is transpose in case of real matrices. Now, when I apply this A onto this circle, so it will become, let us say this object is my someone B. So, U sigma V star into B. So, first I will apply V star on it. So, once I apply V star on it, which is an orthogonal matrix because V is an orthogonal matrix. So, V transpose, then orthogonal matrix rotates the object. So, what will happen? It will rotate this object by some angle based on the value of V transpose. So, now I am having the same circle, but orientation is different. Now, I will apply sigma on it. Once I will apply sigma, so sigma is having scaling factors and those scaling factors are proportional to singular values. So, it will scale this circle and it will deform into an ellipse. If both singular values are equal, sigma 1 equals to sigma 2, it will remain as a circle, otherwise it will become an ellipse, where this distance will be sigma 2 and this distance will be means ratio will be sigma 1. After that, what will happen? I will apply U on it. U is again an orthogonal matrix and it will rotate this ellipse in this way. So, this is the geometrical interpretation of singular value decomposition. Here what we are having? We are having two rotations and one scaling. So, in this way we can interpret singular value decomposition, that it is a sequence of transformation, first rotation, then scaling and then rotation. So, this is the geometrical interpretation of singular value decomposition. Now, we will discuss some of the properties of singular value decomposition. So, let A be a m by n real matrix, means having real entries, and rank of A equals to R. Let us consider that the singular value decomposition of A is U sigma V transpose. Now, if the rank A equals to R, then the first R singular values of A will be non-zero. So, what I want to say that rank of a matrix equals to number of non-zero singular values. The range of A, that is the range space of A, is given by the first R columns of the matrix U. So, as you know that A is a m by n matrix. So, it is a linear transformation from Rn to Rm. Okay. So, what will happen? Range of A is given by the first R columns of the matrix U. What will be the size of matrix U? It will be of m by m. So, what will happen? We will be having m dimensional vectors, and how many vectors? R vectors, that is the rank of A. Those m dimensional R vectors, those are the first R columns of m by m matrix U, will give the range space of A, that is they will form the basis of range space of A. Similarly, the null space of A is given by the last n minus R columns of V, that is the solution space of Ax equals to 0. So, what I want to say, what I want to find out, Ax equals to 0 and Ax equals to 0 means u sigma V transpose into x equals to 0. So, from there I can say that it will be 0 when V transpose x equals to 0, because when this matrix will operate with a 0 vector, it will give you 0. And from here what I want to say, that last n minus r columns, n is the size of V, n by n is the size of V and r is the rank. So, last n minus r columns of V form the basis of null space of A. Now, what I want to say in other word, that last n minus r columns means the columns those are associated with the 0 singular values will give you the null space of A. Similarly, if you talk about the range space of A transpose, so you can see easily A equals to u sigma V t. So, A transpose will become transpose of u sigma V transpose, that is V sigma t u transpose. So, now what I want to say, that in the similar way that the range space of A t is given by the first r columns of V, and the null space of A transpose is given by last m minus r. Earlier it was n minus r, here it will be m minus r, because now it will be a transformation from R m to R n, that is A transpose. And by the rank nullity theorem, rank is R, which is equals to A, rank of A equals to rank of A transpose. So, here nullity will become m minus r. So, that is why I am taking these m minus r columns, and these columns are orthogonal, in fact orthonormal, because the matrix U and V are orthogonal matrices. So, they are obviously linearly independent. Okay. So, last m minus r columns of U will form the basis of null space of A transpose, and the range space of A transpose is given by the first r columns of U, V. So, these are some of the properties you can directly, if you are having the singular value decomposition of a transformation or a matrix, you can directly find out range space, null space, rank, nullity, all these kind of things. Another application is how to find what is the relation between Svd and pseudo inverse. So, I am having singular value decomposition as A equals to U s V transpose. Let A is m by n matrix. So, here U will be m by m orthogonal matrix and V will be n by n orthogonal matrix, and S is a m by n matrix. Let rank of A equals to R. So, what I will be having? I will be having sigma 1, sigma 2, sigma r greater than 0, and then rest of the singular values will be 0. Now, what will happen if I calculate A inverse? Because A is a rectangular matrix, so how pseudo inverse I will define here? It will become U. So, I am writing, let us write sigma. So, u sigma v transpose, this become v t inverse sigma plus, that is I am writing for pseudo inverse, and u inverse. As you know, V is an orthogonal matrix. So, V transpose equals to V inverse. So, V transpose inverse will become V transpose transpose, and I can write it V. Then sigma plus and u inverse again, since u is an orthogonal matrix. So, u inverse will become u transpose. So, if u and v transpose are given, you can easily find out v and u transpose. Now, how to write this sigma plus? So, I will tell you how to write this sigma plus. So, let A be a 3 by 3 matrix. I am taking some examples, and singular values are sigma 1, sigma 2 and 0. So, sigma 1, sigma 2 are not equals to 0 here, means I am having 2 non-zero singular values and 1 0. So, in this case what will be sigma? Sigma will be sigma 1 0 0 0, sigma 2 0 and 0 0 0, because your sigma 3 is 0. Now, in this case what will be our sigma plus? It will become 1 upon sigma 1 0 0 0, 1 upon sigma 2 0 0, and like in usual cases, if we are going for inverse, the diagonal matrix is having entries like A1, A2, A3, then inverse will be having diagonal entries 1 upon A1, 1 upon A2 and 1 upon A3, but here it will become 1 upon 0 in this case. So, simply I will replace it by 0. So, if it is less than a very small entry or 0, close to 0 or 0, in that case simply I will replace it by 0, not by the reciprocal value, because that will not be defined or that will become a very large value. So, this is the case of square matrix. If I am having a rectangular matrix, let us say A B 5 by 3 matrix. Okay. In this case, sigma will be something like this: sigma 1 0 0 0, sigma 2 0 0 0, sigma 3 0 0 0 0 0 0. So, this will be our sigma. Now, what will be pseudo inverse of sigma in this case? That is sigma plus, it will become a 3 by 5 matrix, and it will be, first entry will be 1 upon sigma 1. If sigma 1 is non-zero, if sigma 1 is 0, it simply that will be 0 matrix only. Then 0, 1 upon sigma 2 0 0 0 0 0, 1 upon sigma 3 0 0. So, if sigma 3 is 0, let us say it is 0 here. In this case, instead of 1 upon 0, I will write simply here 0. Similarly, if A is 3 by 5 matrix, in this case sigma will be 3 by 5, that is sigma 1 0 0 0 0 0, sigma 2 0 0 0 0 0 and then sigma 3 0 0. In this case, pseudo inverse of sigma will be something like this: 1 upon sigma 1 0 0 0, 1 upon sigma 2 0 0 0, 1 upon sigma 3 0 0 0 0 0 0. And again the same rule, if it is 0 or very close to 0 some of the singular value, we will replace in the pseudo inverse by 0 only. So, in that way you can write sigma plus Rest you know how to find out. If V transpose is there, how to write V and transpose of U, and then by multiplying these V sigma plus and U transpose, you will get the pseudo inverse. Left right in both the cases, only difference will be how to write sigma. Okay, so this is the application of singular value decomposition for calculating the pseudo inverse. Let us see an example of this. So, find the pseudo inverse of A, where A is a 2 by 3 matrix, entities of A are 4, 11, 14, 8, 7 and minus 2. So, first we will find out the singular value decomposition of A, which is given by, this is my matrix U, this is the matrix sigma and this is the matrix V. So, here if you see that U is minus 3 upon square root 10, 1 upon square root 10, minus 1 upon square root 10 and minus 3 upon square root 10. Here I am having singular values of A as 6 root 10 and 3 root 10, and these are coming from the eigenvalues of A transpose A. So, if you calculate or A transpose, so A transpose will be a 2 by 2 matrix and eigenvalue of that will be 360 and 90. If you are going for A transpose A, it will become a 3 by 3 matrix and eigenvalue will be 360 again, 90 and 0, because one dimension is increasing and it is having rank 2. So, obviously third eigenvalue will be 0. So, I am having this sigma 1 0 0 0 sigma 2 0, and then this is my matrix V. So, if you carefully see, the columns of these matrices are orthonormal, that is pairwise orthonormal, they form a set of orthonormal vectors. Now, in the previous slide we have seen that the pseudo inverse of A is given by V sigma plus U transpose. So, here I am writing U and transpose here, this is my matrix V. So, I am writing as such, and then this will become, it is of size 2 by 3. So, sigma plus will be of size 3 by 2 and it will become 1 upon 6 root 10 0 0 1 upon 3 root 10 0 0, and if you multiply these matrices you will get pseudo inverse and it comes out to be minus 0.0056, 0.0722, 0.0222, 0.0444, 0.0556 and minus 0.0556. Okay. And if you calculate here A into pseudo inverse of A, you will get, you can verify that you will get the identity matrix of order 2. That is why it is the right pseudo inverse here in this case. So, this is the example, means application of singular value decomposition for calculating pseudo inverse. Another application, the same matrix I am having, and find the range space of A and null space of A. So, if you recall from one of the previous slide, the range space of A is given by the first R columns of matrix U, where U is a orthogonal matrix and R is the rank of A. So, hence this is my matrix A. So, hence range space of A is given by, just I have not taken normalized one, minus 3 minus 1, that is the first column, and the second column is 1 and minus 3. So, these two vectors in R2 are linearly independent and they are forming the range space of the matrix A. Similarly, null space of A is given by the last n minus r columns of the matrix V. Here n is 3, r is 2. So, last one column. So, last one column is minus 2 by 3, 2 by 3, minus 1 by 3. So, if I am not normalizing it, I can write it simply minus 2, 2 and minus 1. So, hence rank of A is 2, nullity of A is 1. So, rank plus nullity equals to the vector space R3, which is because A is a linear transformation from R3 to R2. So, in that way, if singular value decomposition is given, you can easily find the basis and basis for range space as well as null space. Now, come to the second part of this lecture. So, just again consider that you are having two vector spaces V and W defined over the field F, and now define a set of linear transformation tau for having all the linear transformation from V to W. So, tau is the set containing all the linear transformations defined from vector space V to vector space W. So, if you carefully see, the set tau forms a vector space over the field F, you can verify it easily because 0 transformation will be there, it will be closure, it will form an abelian group with respect to addition of linear transformation and so on. Now, define the operator norm T operator norm as maximum x belongs to V and x is non-zero, norm of T x with respect to W upon norm of x with respect to V, because T x will be the vectors in vector space W. This norm is called the operator norm on the space tau, where tau is a space of linear transformations. So, let us understand it in other way in terms of the matrix. So, I am having a matrix A which is of order m by n having real entries. We define the matrix P norm as, so P norm of A equals to maximum x naught equals to 0 Ax P upon x, and here this particular we can generalize it for different values of P. For example, if I take P equals to 1, then this become the matrix 1 norm, okay, and it is given by the maximum 1 to j to n summation I equals to 1 to m and absolute Aij. So, what this one is saying? So, if you carefully see it, I am running this summation over I from 1 to m. So, I am taking the sum of the columns, and what kind? If you are having negative entry, I am taking the absolute value. For each columns, I am taking the sum of the absolute entries of individual columns, and then I am taking the maximum one. Similarly, you are having the infinity matrix norm, and just what we are doing in this case, instead of column sum, I am taking the row sum, and out of this whatever row is giving me the maximum sum, I am taking that as the infinity norm. Another norm is that is called spectral norm, that is given by the largest absolute eigenvalue or the singular value, largest singular value. So, spectral norm is nothing just the spectral radius of the matrix, because what will be the spectral radius? It will be the largest absolute eigenvalue. So, as I told you, this is in terms of eigenvalue we can write in this way, and this 2 norm is also called spectral norm. As I told you, we are having Propeneous norm of the matrix A, and Propeneous norm is nothing just the square root of the sum of the square of the singular values, and that will be nothing just square root of the trace of A transpose A, as I am giving here. So, these are different norms which we are defining over the matrix, and all these norms are having own importance, we will see later. A matrix norm is said to be unitary invariant if the norm of UAV equals to norm of A, and that is norm of sigma in singular value decomposition of A. for all orthogonal matrices U and V of appropriate size. Appropriate size means where this product is defined. So, let us take an example. So, find the different norms of the matrix. So, my example is of the matrix, and what are the entities of matrix? 0 1 1. So, first column is 0 1 1, sorry, first row, and second row is root 2 2 0, and third row is again 0 1 1. So, let us say this is my matrix A. So, first let us take one norm. So, one norm will be maximum of column sum. So, what is the sum of first column? Root 2. Sum of second column is 1 plus 2 plus 1 4, and third column is again 1 plus 1 2. So, here this comes out to be 4. Please note that if I am having minus 1 here, still it will become the 4 because I am taking the absolute value. So, at this moment I am taking as such plus. Okay. Now, infinity norm will become the row sum. So, it will be maximum. Sum of first row is 2, sum of second row is 2 plus root 2, and sum of third row is again 2. So, it comes out to be 2 plus root 2. Similarly, the spectral norm will be the maximum absolute eigenvalue of A or sigma 1 of A, that is the largest singular value of A, that is the equal, both are the same thing. So, in this case if I check here, it comes out to be 2 root 2. So, you can verify it easily. Now, if I talk about the Propeneous norm, so it will be square root of trace of A transpose A. So, let us first calculate A transpose A. So, A transpose A equals to 0 1 1 root 2 2 0 and 0 1 1, and then I am having A will be 0 1 1 root 2 2 0 and 0 1 1. So, this comes out to be 2 root 2 and then 0 1 0 2 root 2 1 plus 4 plus 1 6, and this will be 2, then 0, this will be 2, and this will become 2. So, here trace of this comes out to be 2 plus 6 plus 2, that is 10. So, it will become square root 10, that is the Propeneous norm of the matrix A. So, in this lecture we have learned some applications of singular values, that how to find out range space, null space of a given matrix using the singular value decomposition, how to calculate pseudo inverse using singular value decomposition, and then we have defined some of the matrix norm, and we have seen by the help of an example that how to calculate all those. In the next lecture we will again see a very important application of singular value decomposition in machine learning, that is the low rank approximation. These are the references for this lecture. Thank you.